warm-up for graphing. So 4 to the x power, what'd you get for an answer there? 64. So we're just going to substitute the 3 in for our x. And again, I mentioned it's an exponent. It's not 4 times 3. It's 4 raised to the third power. And I think everyone got this one okay. It's 4 times 4 times 4, 64. Now f of negative 2. Now if you just went ahead and put these right in your calculator, that's going to be fine for your graphing. That's going to take care of what you need for your graphing. If it was just an evaluate problem, though, you would need an exact answer, not a rounded answer. So we're going to get the exact answer first, and then we can get a decimal approximation. So same thing. We'd start by substituting the negative 2 in for our exponent. And how do we make those negative exponents positive? 1 over, and it's 1 over the whole thing, so 1 over 4 squared. So the whole 4 squared moves to the denominator. So we're looking at 1, and 4 times 4 is 16, so 1/16. But if you initially just put it into your calculator, or if you then divided that because you need a decimal to graph, we'd be looking at 0.0625. Someone actually has an exact decimal as well. So we don't even have to round that one. It just works out. Now when we graph today, it would be okay to go right from this to your decimal if you were using a calculator. You can use a calculator to evaluate these for your graphs. I don't have any problem with that. But we'll talk about the exact answers as well. Now the fractions can be a little bit trickier looking. Again, you may use a calculator to evaluate it. So when we want f of 3 here, we're going to take that 1/3 and raise it to the third power. And there's a couple of different ways. I saw people trying to evaluate these. So I saw someone say, well, the third power means I multiply it by itself 3 times, so just 1/3 times 1/3 times 1/3. Absolutely, that's our kind of definition of our exponent. If you also remember, when we have a fraction, we raise it to a power. What do we do with the exponent? This is back in 10.2, I think. Begins with a D. Distribute it. So that was our other option that we talked about a little bit. We could do 1 to the third power over 3 to the third power, and then evaluate them separately. So 1 to the third power is just 1 times 1 times 1, just 1. And then 3 to the third power is 27. Or if you took the whole thing and you put it in your calculator, you'd get approximately, so we would have to round here, 0.037. So for graphing, it'd be okay to write the 0.037. I know sometimes on your final they had problems where you had to evaluate, and if it wasn't an exact decimal, I wouldn't want a rounded answer. I'd want that exact fraction. So we can use that same property on the next one, and the answer might be a little bit surprising, but let's see why it works. So if you just put this in your calculator, you probably got an answer. Maybe you trusted it, maybe you didn't. So we have a negative second power. Let's use that same property of thinking about like distributing our exponents. So I'm going to take 1, raise it to the negative second power, and take 3 and raise it to the negative second power. But we can't evaluate negative exponents. How do we make negative exponents positive? We flip them. We move them around. So like here, we took the negative exponent and its base, and we moved it down. So here, when I have a negative exponent at its base, I'm going to move it down to the denominator. So this has got to go down so that it becomes 1 squared. How about the 3 to the negative 2? It starts in the denominator. Where can I write it so that it has a positive exponent? In the numerator. So you just move it top to bottom, bottom to top. So then this is going to come up. Because they both have negative exponents, they're just going to switch places. So most of the time we had a term that started in the numerator, so we sent it to the denominator, but it works both ways. If your negative exponent starts in the denominator, you move it up to the numerator. So just switch where it is. And now that I have the positive exponents, I can evaluate it. So 3 squared is 9, 1 squared is 1, and 9 over 1 is 9. So you might have entered that in your calculator and been like, 9, that seems kind of weird. You don't expect to see, especially a fraction and a negative exponent, give you a whole number, but it happens. And that's why. It's just our properties of exponents at work. But for your graphing, if you can enter these in your calculator and you can get the correct answers back, then that's going to be all you need for the graphing portion. So any questions on our evaluating? Again, got to go back a little to 8.1, concepts from 10.2 in there, but nothing new. Oops. So today what we're going to do is we're going to use that to graph our exponentials. If you want to take out 12.1, in chapter 12, 12.1. So once we know the basic shape and kind of the basic properties, all we're going to have to do is plug and chug. Put numbers in, get numbers back. Put numbers in, get numbers back to draw our graphs of exponentials. So first, let's talk about the general shape. So here's what an exponential function looks like. It's in this form. F of x equals b to the x. So that base is a number. It has to be greater than 0, but it cannot be 1. And x is a real number. So it's just the number raised to the power x. That's what an exponential looks like. So like 4 to the x, 1/3 to the x, those were a number raised to the x. So if we have just a general f of x equals b to the x and b is greater than 1, we're going to get an exponential growth, which starts out what looks like kind of flat and then grows really quickly. So this is what we call an exponential growth. So if you ever hear something grows exponentially, that's what its graph will look like. Now, if we had a base between 0 and 1, so this right here means it's a fraction. Like the 1/3 to the x. Then we have an exponential decay, so we flip that around and it comes down really steep and then levels out. And this is an exponential decay. Now those graphs can be moved around. They're not always sitting right there. But if you have just a regular b to the x, so there's nothing else with your exponent, there's nothing else that's added on to the end of that. Let's talk about the domain and the range. So we're going to have to identify domain and range for all of our graphs as well. So domain is which values? X. So that's going left to right. So the x-axis runs horizontally, so we're looking for the left of the graph and the right of the graph. It's the best way to think about it. So if I look at this graph right here, where's it going to the left? Negative infinity. It's going to keep going all the way back. Now, it's going straight up, or it's not going straight up, sorry. It's going up, but it's always getting a little and a little wider. So even though it's going up really steep, it never goes completely vertical. It gets a little wider, a little wider, a little wider the further we go out. So if it's going to keep getting wider in the positive x direction, what do you think the domain's going to? Positive infinity. Here's the nice thing about exponentials. Just like quadratics, your domain is always negative infinity to positive infinity. So it's another nice one where we know our domain. It's our negative infinity to positive infinity. Now the range is a little trickier because there's something you have to know about the range. So if you miss this day and you don't know this fact, you might get part of this wrong. Wherever the tail levels out, it never actually reaches that value. So wherever our tail looks like it's flattening, I call it the tail. I call the flat part where it keeps going the tail. So sometimes that confuses people. I call this the tail because it's where it levels out. Whatever value it looks like it's leveling out at, it never actually reaches it. So just for our basic b to the x, this is leveling out, and it's almost getting to the x-axis, which has what y value? 0. But we never can get there. So it'll look really, really close. Our pictures might even look like it's there because it's a picture, it's approximate. But if I want to say my range, the bottom of my graph, so we always look bottom to top. If I say the bottom of my graph is at a y value of 0, but it never gets there, it gets as close as possible without actually getting there, how might I use one of my symbols to show that I'm not actually including 0, but I'm really, really close? What do we use to say we don't include it? Parenthesis. So an important part of the range on your exponentials is that you don't include the number. You don't include whatever that base number is there. And then if I look for the top of this graph, where's the top of this graph going? Infinity. So that's a little bit different than the quadratics, because on the quadratics we get to the vertex, so we use the square bracket, but on exponentials we do not. On exponentials you always use the parenthesis. So how about for our decay, our basic decay? What's our domain? Negative infinity to positive infinity. That's going to be for all of our exponentials. No trouble areas on these. All right, let's look for our range. So we're looking for the bottom of the graph and then the top of the graph. So mine's floating a little bit too much probably. Should be as close to the x-axis as possible without actually touching. But that's where the top's going to be. Where's the bottom? What's the smallest y value? 0. Again, my picture should be a little closer. We're going to start at 0, and then where's the top going? Infinity. So even though the picture's flipped around, make sure you always put the smallest value first and largest value second. So this graph actually has the same domain and range. And before we go on, I don't think I moved the notes around. I really should at some point. Before we go to drawing our graphs, let's just skip down to the bottom part where we just keep going with this idea of domain and range, and then we'll draw the graphs. So we're on a roll. So here's a bunch of different exponential graphs. So we've got some growths, we've got a decay, and this time they've been shifted all around. So it was a Union Pulling that was talking about graph shifting last time. Yeah. So these are some shifts, some vertical, and this one's a horizontal shift. You don't have to worry about that part. We're just going to talk about the domain and range. So on the first graph, it's an exponential. It's got that swoosh that really, it goes up really quick. What is the domain of all of our exponentials? Negative infinity to positive infinity. So all of our exponential graphs, if you can see that's our exponential, it goes up really quick or comes down really quick with that one big swoosh. It's an exponential, our domain, negative infinity to positive infinity. Also, if you look at the equation here, the x is in the exponent. That's an exponential. If the variable is part of the exponent, that's an exponential. The domain is negative infinity to positive infinity. Now the range is going to change. So what we're looking for is the bottom of the graph and then the top of the graph. So if I look at this graph, okay, I've got the bottom. It's coming down right here. I want to look at this part where it levels out and see what y value that's at. So what's the y value where that levels out? -3. Not where it crosses. Now, and not necessarily that's what you're looking at, but that is a common mistake is people look for where it crosses the y-axis. It's not where it crosses, it's just the lowest point in the graph. So I'm going to start at -3. But a property of exponentials is we never get there. We get really, 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 really close. We never get there. So you always use parentheses with your exponentials. And then where's the top of the graph? Infinity. Now another note of where, if you're given the function explicitly, of where you can get your range, this number right here. The big number on the end will tell you where your range starts. So second graph, all right, domain. Negative infinity to positive infinity. All right, range, we want to find the bottom of the graph. So we've got the graph flattening out. We want to find that tail that flattens out. 2. And again, look at where that is in your equation. And where's the top of this graph? Infinity. We don't include the 2. So we use parentheses. Questions, Sarah? I don't want to say yes, but let me see. Check your homework. I think they do. Now, the other thing is sometimes you have to draw the graph and then tell the domain and range, but you could do the same thing. Look for the big number on the end. Yeah, on your homework they always give you the equation. All right, last one. What's my domain? Negative infinity to infinity. Hopefully we get that one right. If you have an exponential, now how do we know it's an exponential? This is a good question because we're going to do a lot of exponentials from now to the end of class. Where's the x? It's where the x is that tells us it's an exponential. In the exponent, it's the power, yes. That's what makes an exponential. The x is the exponent. The variable's in the exponent. So now we want to find the range. That's the part that changes. So bottom of the graph, top of the graph. So here's the leveling out area. What's the y value there? 0. Now, if you're looking at, and we use a parenthesis, that's not the best parenthesis. Let me draw a more clear parenthesis. Where's the top of the graph? Infinity. Now, you might look at that and say, wait, I see a +1 in my equation. But the +1 is part of the exponent. The time that you get a different, it's a vertical shift is what that is when you have that big number on the end, that's when you change your range. Your standard range is 0 to infinity. So you see how this has no big number on the end? Everything's part of the exponent. So it's really, if you're thinking about it, it's really like a +0. Nothing's added to it. This is our standard kind of domain and range. It's only if we have the big number added or subtracted on the end that we switch the range. So don't look in the exponent for your range. It's only if there's an extra number added or subtracted on the end that it ever changes. But also, if you just look for the flat area, find that y value, that's your range. Bottom of your range. Questions? And we'll find the domain and range of the graphs we draw today, too. All right, so let's draw. We're going to start with this one. All right, so graph the function by making a table of coordinates. F of x equals 3 to the x plus 1. Now, I believe on your final exam review, and if they ask for this on your final, they want a minimum of 5 points. We're going to find 5 points for all of these, at least 5 points. On your homework, the directions say using -2 to 2 inclusive. What that means is they want you to make, so we're going to make a table. They want you, when your homework says -2 to 2 inclusive, they just want you to pick the x values, -2, -1, 0, 1, 2. Which, if you get this problem on your final exam, that would cover requiring 5 points. So it doesn't have to be those, but those will work well for this class. If you just do -2 up to 2. Gets you 5 points, gets you some negatives, your 0, and some positives. So what we're going to do now to find the other half of the point, because every point has 2 halves, right? What are the 2 halves? We have x, and what else do we need? Y. So we got to find y. And to find y, all we're going to do is we're going to take our function, and just like we did in warm-up today, we're going to replace the exponent with our number. So we're going to start with -2. So we're just going to go in and we're going to replace our x with -2. And then we're going to add 1 to that answer. Now again, you could just grab your calculator and find this value as a decimal. Because when you graph, decimal is probably going to work better for us. If you're looking for the exact answer, you would start by making that 3 to the -2, 1 over 3 squared plus 1. So 1/9 plus 1. It's 1 and 1/9. Or sometimes people make more complicated than it has to be. 1/9 plus 1 is just 1 and 1/9. So we just work out that 3 to the -2 like we always did. We do 1 over 3 squared, which is 1/9. But in this particular function, we have to take that answer and add 1 to it. So you get 1 and 1/9. So when you graph, you probably can graph 1 1/9. Like that wouldn't be too hard to approximate. But you may also want to take your calculator, or if you just use your calculator from the start, you're going to get that that's approximately 1.11. So my fat pen makes this hard. I usually put this as a third column. But so my first point, my x value is -2, and then my y value worked out to be about 1.11. So if I go to my graph, I'm going to go on the x-axis, I'm going to go back to -2, and then I'm going to go up 1 and then just a little bit more. Okay, we're not launching rockets off these graphs, we're approximating. So it's going to be -2 and then up a little bit above 1. So we go back -2 and then up just a little bit above 1. So that's a 1.1. And then we're going to repeat the process. We're going to take f of -1, so we're going to replace our x with a -1. And you could put that in your calculator all at once, or if we're looking at where it comes from, we got to make that exponent positive. So it's 1/3 plus 1. So it's 1/3 plus 1 gives me what? 1 1/3. So if you're adding a fraction to a whole number, you just put them together. 1 1/3. Which you could probably graph. You can approximate a third of the way up. Or if you like your decimals better, just put it in a calculator. It's about 1.33. So the x value is the value we started with, the -1, and the y value is the number we get back. So there's another point on my graph. So I'm going to go to my graph, and I'm going to go -1 in the x direction, and then go up about 1 1/3 in the y direction. So it's just a little bit higher than the first point, which it can be hard for my big dots to show that, but so it's just a little bit higher, not much. 0.22 higher. And then we're going to do it again. So for 0, we're going to take 0 and we're going to plug it into our function. So we're going to do 3 to the 0 plus 1. Rules of exponents, 10.2. What's anything to the 0 power? 1. And that's a lot of these graphs have mistakes because people don't remember that. Anything to the 0 power is 1. So sometimes they get exponentials that instead of being a nice curve, they bump down and then they curve up. It should be a nice curve. So this is 1 plus 1, 2. So my point is 0 for the x and then 2 for the y. So that one's going to be easier to graph since it's not a decimal. But you can start to see we got a little curve forming. Little curves coming out of those points. So to find the y value for 1, these graphs aren't exciting. You take 1, you plug it back into the function. So we're looking now for f of 1 is 3 to the 1st plus 1 gives me 3 plus 1, which is 4. So my point, the x value is 1, the y value is 4. So I'm going to go over 1 in the x direction and then up 4 in the y direction. You can see we got a little more curve coming in. And then last, for 2, we're just going to substitute 2 in. So it's 3 squared plus 1 gives me 9 plus 1. It's just barely going to fit on this grid. 10. So my point is 2, 10. So I'm over 2 and up 10. So any questions? We still got to connect these, but any questions on finding the points? It's just our function notation. Take your x, plug it in, get your y. Take your x, plug it in, get your y. Take your 5 times. And again, you may use a calculator to evaluate these. I don't need to see all this work. I just want to see your points, plot them, connect them. Anna. Yeah. Nope. Sarah. For this class, these are good x's to choose. Like in life, you can choose any x's realistically, but you're going to need a minimum of 5 in most of your directions. So if you just pick those 5, you'll be good. So now we got to connect these. We got to draw this curve. But remember, the exponentials kind of level out. If I look at my function, what value is this graph going to level out at? Think about the range of the function. We talked about looking at the equation for the range. It's going to level out at 1. Remember, we use that big if there's a big extra number on the end. So when we draw our graph, make sure your tail kind of flattens out at 1. So this is where we know our tail's going to flatten out at 1. So I'm going to just kind of come in along that 1, connect my points. So what's the domain of this graph? Negative infinity to positive infinity. Where does the range of this graph start? 1. It's that big number on the end. Do I include it, not include it? Parentheses, not include it. And the top of this graph? Infinity. So we're going to use that big number on the end. Tells us a lot. It tells us where to kind of level our graph out when we draw it. It tells us where our range starts. If you don't have a big number on the end, it's just 0. It's 0 if you don't have that big number on the end. Questions? All right, here's the full directions from your homework. Graph functions f and g in the same rectangular coordinate plane, so that means just on the same grid. Select integers negative 2 to 2 inclusive for x, so that's just negative 2, negative 1, 0, 1, 2. Then describe how the graph of f or of g is related to f. That part I'm not so concerned with. The describe part I'm not as concerned with as that you can draw the graphs. So if you can get your graphs, then we're all set. I'm actually going to start with g of x. We'll do f of x second. So let's start with g of x because I just want to show you how g of x is different than our previous example. So we have to graph both of them. Let's start with g of x. So I'm going to make my table. So I'm going negative 2, negative 1, 0, 1, 2. And I'm going to start with g of x equals 2 to the x plus 2. And then we're going to need a whole separate table when we want to graph f of x. And again, on your homework, you could certainly start with f of x. I just want to compare g of x to the previous example. So we'll start with it. So these are graphing exponentials. And how do we know, again, it's an exponential? What's it look like? It's got an exponent, but there's something special about the exponent. Because, like, yeah, the exponent's ex. Because, like, quadratics have an exponent, but the exponent's 2. The exponent's a number. So it's an exponential because the x is in the exponent. So we know we're going to have one of those curves. And we're just going to plot it by points. Plug and chug. Put the number in, get the number out. Put the number in, get the number out. So let's start with a negative 2. So g of negative 2 is 2 to the negative 2 plus 2. Notice all of the little numbers are in the exponent this time. That there's no big number on the end. This is all part of the exponent. So what we're going to do is we're actually going to always start by combining the exponent. So if you've got something to do in the exponent, you've got to combine that first. So we have our base of 2, and then what's our exponent if it's negative 2 plus 2? 0. Just add those together. So we have 2 to the 0, which is 1. Anything to the 0 power is 1. So I probably have room here to make my point column. So my first point is at negative 2, 1. So if there's no big number on the end, work out that exponent first. So I'm over at negative 2 up 1. And then we're going to do the same thing for g of negative 1. So I'm going to take 2 to the negative 1 plus 2. And all of that little addition work is in the exponent this time, versus last time where the big number was added afterwards. So we're looking at 2 to the first power, which is 2. So my next point is at negative 1, 2. So back 1, up 2. And then we're going to do it again. G of 0 is 2 to the 0 plus 2, which is 2 to what power? 2. 2 to the second, which gives me 4. So my point is 0, 4. And then we're going to do it again. These aren't exciting. I know some graphing is really exciting. These graphs aren't very exciting. So 2 to the first plus 2. Again, all in the exponent this time. Notice how it's written differently than before. So it's 2 to the third, 8. This graph doesn't fit. 1, 8. So over 1 and up 8. And then g of 2 is 2 to the 2 plus 2. Everything's in the exponent, so we combine that first, which is 2 to the fourth, which is 16. So our point is 216. Our grid only goes to 10. So 2. I'll just put 216 out there. Normally it would be better to like select another value back. So like put a negative 3 in for x. This doesn't fit, but we'll just follow the directions, which say to use 2 to negative 2. All right, now we've got to connect it, and an important part of connecting it is where does it level out? 0. How do we know it's 0? Yeah, there's no big number on the end. Everything was within the exponent. So if there's no big number on the end, we can assume it was a 0. It's adding 0 doesn't change it. So our graph is going to level out at that x-axis. So what's the domain of this first graph? Negative infinity to positive infinity. Domain's not changing. The domain for all of these will be negative infinity to positive infinity. What's the range? Where does this graph start? 0 up to infinity. So take a minute and work on your points for f of x. If you don't have them already, try to find those points for f of x. All right, since we're getting short on time, and it looks like everyone's at least got the idea, because you got to do the negatives first, and if I see those correct, hopefully you can do the positives as well. So your negative exponents, so f of negative 2 is 2 to the negative second power, which if you're working it out by hand is 1 over 2 squared, 1/4, or 0.25. Really, you could use any of those to graph, so negative 2.25. Now when you graph it, it's going to be approximate. I'll draw my graph in blue. Negative 2 and then up 1/4. Just a little bit. And then you do it again with a negative 1. It's 2 to the negative first, which is 1 over 2, which is 0.5 if you're working with decimals. And decimals are fine for graphs. Nothing wrong with decimals when we're graphing. So negative 1 and halfway between 0 and 1. F of 0, most fifth point. Anything to the 0 power is 1. Sometimes they get the 0.00 and you'll see your graph has a dip where it shouldn't. So everything should keep going up just a little bit and then a little bit more. F of 1 is 2 to the first, which is 2. So I have the point 1, 2 over 1 up 2. We can really start to see our curve coming out. And then f of 2 is 2 squared, which is 4. So the 0.24, so over 2 up 4. And for this graph, actually, more points fit on there if you wanted to get it a little bit more. But question of the hour, where does this graph level out? 0 again. So make sure when you draw that first part, it's at 0, and then we're going to go up from there. So what's the domain of the blue graph? Negative infinity to positive infinity. And what's the range? 0 to infinity again. Since neither of these had a big number added on the end, they actually have the same domain and range. So the things I really want you to focus on, again, on your homework, don't worry about the then describe how the graphs are different. I want you to focus on drawing the graphs and identifying the domain and range of them.